Hello. So we're going to try to start on time. I have a lot of materials, and hopefully you guys will last through the whole talk. Welcome to Destiny's Multithreaded Render Architecture talk. My name is Natalya Tatarchuk, and I'm a graphics engineering architect at Bungie. Today's talk, I want to warn right away, is not about shader tricks. It is not about specific graphics techniques or other sexiness. We covered a fair amount of that in previous presentation at GDC and SIGGRAPH, and you can download a bunch of them from the Advances website. And these slides also will be on the Advances website, so if you miss some diagrams or some information, you can look it up there. Now for this talk, I'm going to assume that you have some familiarity with task-based parallelism concepts. So I'm not going to focus on job manager designs, on synchronization primitives, on threading, etc. Now, I also recommend that you check out Barry Genova's talk on the foundations of the Destiny threaded model, because he covers a lot of the base concepts that I rely on in the design of our renderer. Now, today, what I will do is cover the Destiny core rendering architecture. Specifically, I'm going to talk about how the engine data flows all the way from game state to the GPU, about how we approach renderer jobification, all of the concerns for task and data parallel execution, including dynamic load balancing, latency reduction techniques, as well as jitter, and also how did we keep GPU fully saturated at all times, getting rid of GPU bubbles as a continuous topic throughout development. I'll also touch on architectural principles that helped us encapsulate some of the complexity of the multi-threaded design and let our graphics engineers focus on what they do best, writing graphics features. Now, if there's anything I want you to walk away from this talk, and that is that creating a data-driven pipelined architecture allows you a lot of flexibility for creating graphics features as you go, and also allows you to help optimize performance for a variety of platforms and create cross-platform implementation for features. So the outline of this talk is as follows. We're going to do a quick breakdown of coarse-grained parallelism. We're going to talk about the goals that we set out for the Destiny architecture. We'll dive deeply into the details of this architecture, and then draw conclusions about what we've achieved. So I know most of you are familiar with this, but let's do a super quick overview of what happens in the frame in a game. Of course, we're going to run our simulation. This is the beginning of a game tick. AI, physics, animation, and any code that affects the gameplay computations. Then we use the simulation data to determine what is visible in our view. This can be visibility computations or just a raw list of visible objects, for example, in UI or in cinematics. We use these elements to generate GPU commands. This is the traditional CPU submit operation. Now, the result of this is GPU command buffers that will flush to the GPU, which crunches on them to output the back buffer, which will flip to display to the player the very next available vsync. This is pretty straightforward. And it maps pretty well to what's called a system-on-a-thread pipelined architecture. We shipped with that approach for our Halo engine. Now, in Halo Reach, we mapped major game functions to a small number of threads, which is what you see here. Now, we had unique threads for rendering, audio, simulation, where each CPU thread was essentially mapped to a hardware thread. A different way to view this execution is by looking at the frame tick diagram. Now, here you see, as we go through the game tick n, simulation computes game tick data, and then we're rendering the previous frame in the meantime. That's the run of the CPU submit that I mentioned. Once the simulation has finished, we copy the game state, the entire data, to start rendering this frame during the next game tick. In Halo games, all output systems processing begin only after the simulation has completed its work for the current tick, and then we copy the full game state. We ran serialized visibility computation at the start of each render submit operation. Now, until visibility is done, we actually can't start generating draw calls, so we can't feed the GPU. One of the problems with system on a thread is that you have suboptimal workload distributions. For heavy workhorses, for example, rendering and simulation threads, you would see very heavy utilization consistently. But a lot of threads saw a fairly huge amount of idle time, which is, of course, bad. Now, this approach also doesn't scale well to heterogeneous platforms such as PS3. Different core layouts and additional hardware cores would not actually support in this model. We also pay for a full copy of the game state, which of course includes a ton of data we, the rendering guys, don't care about. I don't need the pathfinding data or the animation state machines. On memory-constrained problems, this was quite a bit of an issue. Serialized visibility computation also means that, again, if we didn't pipeline it correctly, we would see GPU bubbles in certain frames and potentially longer latency. But the plus side of this design is that it's darn simple to use. It is super extensible, and of course, it's convenient to code for it, serialized execution for the rendering. It doesn't exhibit any complex concurrency problems because this threading model is super straightforward. Now, we overlap simulation and rendering, which means that we can do more work in each phase. When you have complex AI and physics computation and animation, and your simulation can take up the full workload budget and heavy rendering workloads, this pipelining is very important. So with all of this in mind, what were the goals we set out for the renderer engine, for Destiny? Of course, the most important goal is, well, we want to ship the bloody game. So we want to ship a fun game with great visuals and responsive gameplay, which of course translates to low latency. Destiny's worlds are complex, alive, and beautiful. Our players explore large destinations with diverse environments, with lush vegetations, and a lot of features, which means that our renderer needed to have high-quality lighting, dynamic time of day, real-time shadows, high-resolution rendering, weather elements, rain, snow, tree rendering, and many other features. To make this happen, we implemented a variety of them. And here is a teaser in case you haven't seen Destiny. So with all this graphic sweetness, we needed an engine with rock-solid performance. This was super important for all of our platforms, consistency of that performance. And so we needed an engine that would be scalable across several console generations, and ideally also last beyond what's currently available. Now, of course, we see quite a bit of a difference in CPU design, as you see some of the specs here, and GPU designs across console generations are even more varied. And so this introduced a fair amount of challenges for our system design that our architecture had to cope with. At the same time, as I mentioned, Destiny is a fun, fast-paced sandbox game with highly responsive gameplay, which means consistently low input latency is required. And that's latency from the time the player presses a button and when they see the response on the screen. Any sandbox game can have a lot of variability in workloads. You can have frames with very little CPU simulation and very heavy CPU submit and GPU workload, as what you see here, mixed with a frame where CPU and GPU might take a little break. And then, of course, during the big battle scenes, you'll see both of them brought to their knees, and our engine and renderer has to keep up with the dynamic workloads, which required us to have very efficient load balancing. Now, to ship on last-gen consoles without sacrificing the gameplay mean that we had to squeeze every millisecond from every available execution unit. To do that, we moved everything on the renderer and visibility workloads into jobs, used dynamic load balancing, and also smart job batching to get the best occupancy from both CPU and GPU, and to keep our latency low. Now, personally, a major goal of rendering architecture was to keep the API simple. All of this dynamic load balancing introduces a lot of complexity for the threading design. And we wanted, like I mentioned, to have graphics engineers write leaf features without worrying about all of that complexity. We had a ton of features to write for a lot of platforms, and we wanted to create them quickly and automatically jobify them. We also wanted to decouple game state traversal from rendering, which allows us to improve latency and help make the rendering submission a data-driven, streamlined kernel processor. Now, this data-driven rendering pipeline allows us to have render passes executed via jobs that are operating on individual render elements arranged in coherent caches rather than directly on game objects. So when all of this is put together, the execution of the renderer looks something like this. This is an actual job diagram from our shipping Cosmodrome level on Xbox One. We start by simulating game text, so you see a few simulation jobs. Of course, it's fairly challenging to jobify the simulation secret sauce workloads. Then we run our visibility workloads for a variety of views to determine what should be rendered in this frame. We used Ombre visibility in a Destiny engine, and last year GDC covered a lot of the details for how we implemented the visibility computation in our engine. Next, we're going to extract current game state only for visible elements into a dynamic data structure we call frame packet. We're going to convert this data to GPU-friendly formats ready to be slammed into GPU registers during the render prepare phase. And then finally, using this GPU-friendly data, we're going to generate the GPU command buffers for the, in other words, draw calls during render submit. This also goes wide to keep the latency low. Now, it was important to have well-defined synchronization points, which are necessary to ensure that we have safe and well-defined concurrent data access across each phase of the execution. Now, here's an example from, this is the job telemetry from PS3. Noted the distribution of jobs on PPU, and then we also have a number of jobs running on SPU. So mapping the previous diagram, this is the set of jobs that runs the simulation. You see that it's very heavily occupying PPUs. We have our visibility workloads, which run solely on SPUs. We extract game state. During this phase, we occupied every unit that we have available. We then run render simulations and prepare GPU-friendly data, again, going on any unit that we can get our hands on. And then finally, generate GPU commands to render this frame. So we had a pretty solid wall of jobs to execute continuously throughout the entire frame. Now, today, I'm only going to focus on this part of our rendering engine. I will not be able to give you all of the details, and especially for the advanced topics, but hopefully I'll give you a taste of what pipeline data-driven architecture is all about. So how did we decouple game state traversal from rendering? We drive all of the workloads by results of the visibility to decouple game objects from rendering. And so in order to do that, we also need to decouple visibility objects from game objects, providing a very thin interface to allow them to communicate. This is what allows us not to traverse game objects for visibility computations. What we store in a game object is not necessarily what we need for rendering. As I said, we don't need AI components, we don't need the animation data. So we only cache the data that we actually need in the renderer. Typically, this will be the static data such as mesh references. For example, for static objects, maybe there are transforms, there are material handles, etc. Most of this data does not change until this object is unloaded from the engine. And so we can cache it in a cache-coherent representation in memory. And we also can ensure that the access to this data is read-only for the duration of the lifespan. For dynamically generated data, we don't need full object. And so we can extract just a small slice of data every frame. We also need to grab data only for what we'll actually render, in other words, visible objects alone. And if the object is not visible, don't bother extracting its data. This lets us save the amount of data that we need to double buffer. It also reduces the amount of data we need to actually copy, reducing the workloads. So if we bring back the Halo engine diagram and modify it for this approach, you'll see that we'll have simulation, followed by visibility, followed by extract, which copies out a much smaller per frame data out of game state, which is then used for rendering this frame. Now, to decouple game systems and visibility, we separate representations into game objects, visibility, and render objects, using thin interfaces to allow them to communicate across different phases of the engine. So we start with a game object. This is just your general biped, for example. Each component will map to a particular render object on the renderer side. When a new game object is added to the world, it registers itself with the renderer, which then caches all the static data, as I mentioned, and then also may cache a game object component. This is the interface that we'll use to communicate during extract. The renderer then returns a handle to the render object back to the game object, which of course caches it locally to the component. Using the render object, we then register with visibility, and then the visibility caches the render object handle, and this is exactly how we're going to drive the visibility and extract pipeline. Now, we actually store the visibility inside the game object component, which means that if we want to hide an element, we simply unregister with the visibility and it stops rendering. Now, the render object doesn't know anything about visibility at all. Only visibility knows about the render object. So we've decoupled game object system, we've decoupled the visibility and render layers, and this is what allows us to drive the entire system from results of visibility without having to access game objects. Now, we store all of the dynamic data, be it extracted or converted to GPU representation, in a custom data structure called frame packet ring buffer. This is a multi-thread allocation safe data structure that is fully stateless. We generate it every frame and we throw it away every frame. Each frame's worth is referred to as a frame packet. It has a fairly small footprint. We stored about 1 megabyte on last-gen consoles, which for comparison is only 9% of the total game state on those consoles. For comparison, for reach, we copied about 10 megabytes every frame to a mirror. So once we do that, how do we go about the actual jobification? So a render pipeline operates on the concept of views. A view is defined by the usual frustum and camera parameters. This is pretty standard. And we have a number of views in our frame. For example, player view, we have shadow views, we can have overhead map views, etc., reflections, and so forth. Now, a view in our system also defines end-to-end render job chain. So the view becomes the jobification unit. So if we look at the simplified form of how the architecture handles views, we start simulating our game tick. We then determine what views we might have for the current frame, and then we generate the frame packet data structure for this frame. We figure out what elements are visible in each view. We populate internal renderer data structures for that view for efficient iterations and subsequent jobs. We extract the game object data into the frame packet. And then at that point, we can tell simulation, hey, you're free to go and do the work for the next game tick. Then we prepare the GPU-friendly data representations. We also run render-specific simulations, cloth, particles, etc. And then we tell the core systems, hey, now we're ready to submit to the GPU. We run our high-level submit scripts. We generate draw calls in individual submit jobs for each view. And once we've completed all the draw call generation, we fire up the present signal, which of course tells the core system that we've completed this frame's submit. Now, we run a few global render system jobs that essentially are executed regardless of what data we have on our frame. These essentially act as the main synchronization point in our system. However, for every single view that we have in a frame, we create a separate view chain. These job chains are data-driven. If you don't have data, for example, for a local light shadow view, we don't generate a view chain for that specific view. And here's an example of the job chain jobs. Now, each engine phase completes by all of the global synchronization jobs. These synchronization jobs are used by the core renderer and the simulation system to control access pattern to the underlying data containers. That's your game objects, the visibility data, and the render objects. The first job we execute is a global job for the frame to compute which views we have. Like I said, this is to figure out first-person view, etc. This job also reserves the frame packet and the view packets within it. So here's an example of that representation. Now, note that for all memory management in the frame packet within the view job chains, we actually don't perform any runtime allocation. In fact, in our engine, we don't do any dynamic allocations at runtime. There are no heavyweight heaps. We simply allocate frame entries and render nodes within the lock-free frame ring buffer. Now, once the views are determined, this job sets up job chains by executing all operations in each view. So next, we begin the extract phase to copy data out of the game state. Now that we have views defined, we run the visibility job for that view. Now, this job operates in visibility objects, that representation that I showed you earlier, and then it returns a list of visible objects. Note that we actually can skip the Ombre computation and run a bypass job that simply gives us a list of visible elements. Since we only need the visible elements until the next job that we run, we store the visible list in a temporary visibility ring buffer that only lives until extract is done. So the next job we're going to run for this view is populate render nodes job. Essentially, this is the job that sets up cache-coherent arrays that the entire pipeline will operate throughout its execution. We call those elements render nodes. This is the efficient representation that is very small, very cache-friendly, and then again, from that point onward, that's what we're using. The populate render nodes job is going to run through visible elements for that view. It sorts them by the render object type for coherency, and then it will reserve and populate the individual arrays that you see here for the visible nodes within each view. Those are called view nodes. They store some view information. This is your bounding sphere distance from camera, et cetera. This data is stored actually in that tiny render node for the view for cache coherency, since we run a lot of tight iteration loops on the render nodes during extract, prepare, and submit. Now, this may introduce a small number of redundancy because, for example, bounding sphere is the same across a variety of views, but we keep it in the render nodes in order to have that data already in the cache when we're iterating and computing different operation. Now, the view node can actually allocate data dynamically in a frame packet if it needs to allocate some very specific data for that frame. Each view node is going to map to a frame node. Now, frame node allows our system to share data across multiple views. For example, we can have multiple views that have a skin character. We don't want to copy skinned matrices multiple times. By putting them in a frame node, we're only going to do this work once, and we have one copy of the data. So we take this even further by allowing the same model for the per object data to share for data for different game objects. And here's an example of this layout. The reason why I'm telling you about all these nodes is because later we're going to map it to a small set of functions that the graphics guys implement, and all of the coherency, all of the data access and jobification is going to be done because they're accessing the right elements in the frame. So for example, for rendering this frame, this is a cinematic shot with the radar character, which you see here. If the radar is present in the player view, then the view node would be our reference to the render object. So this is the example pointing to that. Now, each frame node is going to link back to that render object, the radar in this case, which allows us to access its statically cached data. So how do we extract data out of game state? For each view node in the view packet, we're going to extract data out of game state by essentially iterating coherently over the view nodes, which are sorted by the render object type. We're going to reach into the individual object types extract entry points. And then those jobs only will operate on the individual view node, individual frame node. They will write results solely in the frame packet. And then we also allow reaching into the game object during extract using the handle cached in the render object. Coming back to our friend the radar, we would extract and store its per-view attributes in the view node, and then we're also going to extract its skinning data, its transform in the world, any particular parameters about its state, and then store it in a frame node. Now, we would get this data by reaching out to the game objects. So here's how we walk over to the game object. And then while all of this sounds kind of basic, like I was saying, this is simply the core background for how we structure the individual jobs in order to support safe threaded access. Now, extract phase is the only time that we allow crossing the object system and render a wall, which in our world is kind of like this. It's a tiny little hole, and we don't allow any other access for it. So during extract, we actually generate jobs that go wide across this phase. This is an example of multiple extract jobs for the view, and the jobs are generating with smart batching for different object types. Once extract jobs are finished, we actually tell the simulation, we're done. Go start simulating the next game tick. Now, it's really important to mention latency at this point. As you notice, we can't start doing the game tick until we finish extract. And so we need to make sure that we keep the phases to the minimum in order to reduce the latency. So here's an example. Now, during extract phase, all of the output system, this is not just rendering, this is networking, UI, audio, they're all reading game state. Simulation is paused, they're extracting data, which means that game state is not modified, it's read-only during that phase. So we have to run all of these systems extract as quickly as possible in order to unblock the simulation. During our development, this was actually our most latency critical phase. Extract window for rendering consists of visibility computations for all views and actually a raw copy out of data. So since visibility is CPU work, what can we do to move it out of extract? If you look at visibility, most of the computational workload is in static visibility for the main player view. This is typically when we see the most workload. This is also the most expensive view, and we want to do the most completely accurate visibility computations. For example, shadows are a little bit lighter on the GPU. So let's move out the static environment visibility out of the extract window. If we stagger visibility with simulation, we can achieve that. We start by pulling the controller during simulation. It's important to do that as late as possible so you reduce your input latency. And as soon as we have controller information, we can figure out what views we have in a frame. So once we have that, we're going to run static visibility computations predictably using that information, using the static computation for the player view. Now, static environment doesn't get affected by simulation. It's static by definition. So we can run this in staggered computation with simulation at the same time. And this is an example of the player view. Now, once we've computed the predictive static visibility, we're going to run dynamic visibility. This includes both dynamic objects, so my bipeds, my AI combatants, my players, but it also will include visibility for dynamic views. Maybe we don't know we have a light present that we want to do a local light shadow view. We're only going to do that if we know that that light is actually visible in the main player view. Doing this computation, moving it out of extract, actually saved us about 3 to 4 milliseconds on last-gen consoles and about 2 to 3 milliseconds of latency on current-gen. So it was a very worthwhile effort. Next, we're going to also slim down extract by only focusing on taking data out of game state and ignoring it for that phase. Copy it out, copy out the minimal amount, and don't do any complex transformation to unblock the simulation. Now, we need to convert this data into a GPU-friendly format, and we do this during prepare phase. We're also going to do this computation only for visible elements. Because we're running all of this for after visibility has run, we avoid any extraneous work for elements that won't be seen. Another optimizations that we can do is we can actually use LOD to skip computations that won't be perceivable by the player. This is important in case, for example, I don't want to simulate finger bones for somebody in the back row because, well, we probably won't notice them. So here's an example of a video where we can actually look at some of the computations we do in prepare. We convert the extracted data to GPU representations. So for example, we take the local node transforms for our skinning bones and then convert them, for example, to world space dual quaternion data that's ready to be shoved into the GPU registers. We also run any non-game state affecting simulations. Cloth is an example of that. Particles. We don't want to run those element simulations for things that won't be visible. Now, another thing that was really important for Bungie is to keep very predictable budgets for execution of different workloads. For example, Cloth had to simulate in 2 milliseconds consistently. So during prepare, we design our systems to do bucketing into different LOD levels. For example, even for GPU, we maintain a consistent 1 millisecond for skin data. And this is also where we do all of this bucketing and sorting work. For all of the characters that you see here, all of that workload is happening during prepare. So once you do that, you basically prepare the render-ready data while the simulation is running for the next game tick. This provides us with much better pipelining. So now when the simulation is running in parallel, we're executing the prepare phase. In this case, similar to extract, prepare also operates by iterating through the view nodes. This is, again, on the core render architecture side. It uses the frame nodes corresponding for each view node. It uses the cache render object data, and then executes prepare entry points for different objects. Prepare also writes results into a frame packet. There's an important difference from extract, though. It no longer can access game state. Remember, simulation is ticking. Bringing back our friend the Raider, during prepare, we're going to fetch its view node, and we're going to run Cloth simulations for its tattered cape. We're going to compute all of the non-deterministic computations for animations of the bone, face, if the Raider is really close to our view. We're going to skip all that work if he's far away. We're also going to bucket him based on his vert count into a skinning LOD bucket. Remember that we want to have a predictable skinning GPU performance. And all of that is done in prepare jobs, which are running wide across different render object types. Once we completed all of the prepare, we published this data to be ready to be submitted and created GPU draw calls. Now, the reason why we need this explicit synchronization is because, again, we might have multiple jobs generating the data that we may need to use across different views. So we need to make sure all of that data is completed before we can start submitting it. And this is the synchronization job that runs it. Next, we're going to execute jobs to generate GPU commands. I'll get back to that actually in a second, because it's a fairly complex topic. So when all of the submit jobs are done, we're going to signal to the GPU that we've finished, and this is the call to present. This synchronization point indicates that we're ready to flip the moment GPU has finished the workloads. And also this is for, again, for those memory-constrained platforms, a sign that we're now done with the actual GPU commands ring buffer, and we can start overwriting it with the next frame's worth of GPU commands. Of course, we can repeat this jobification process for all of the view chains, so here's an example of expanding into 3 views. And again, the underlying system does it automatically. So for all this complex job chaining, we need to make sure that the writing of the leaf features is actually easy. This is the bread and butter of graphics code the majority of our graphics team was working on. Every one of us wrote features, myself included. So create the dog food, consume the dog food was a very important architectural principle. And we didn't want to change job dependencies or occupancy or synchronization points anytime we added a new feature. Anytime we added a new platform, for that matter, we really didn't want to muck with the leaf features either. And so the jobification had to be transparent and automatic. And the way that we've done it is via a feature render abstraction. So we talked about a frame rendering as if we have the same types of objects on the rendering side. But of course, we have many different elements in our frame. For example, for this shot, we have static environment instances. We have gear objects. This is the customization system. We have terrain. We have trees and decorator system that populate our environment. And then we have sky dome objects, etc. So all of these elements build up the actual frame. And we want to express this taxonomy in the core renderer architecture by using the render feature encapsulation. You can kind of think of it very simply. It's essentially the same data representation, the same code path equals render feature. And so, for example, most of the skinned elements will need skinning transforms. They're going to need to convert them. They're going to need to shove them into GPU registers in a very specific format, and they're going to need to iterate over mesh parts. Great, this is one feature. A particle system might have a very different data representation and very different logic for draw call generation. That's our second feature. So each feature is implemented with what we called a feature renderer interface. This is essentially the main interface for implementing graphics features in Destiny. This interface defines how we extract the dynamic data, how we convert it into GPU-friendly representation, what simulation we might run on it. It also defines the actual data format we store in the frame packet, all of the nodes that I mentioned to you. And it also defines, of course, the code, how do we render the bloody thing. So it exposes a number of entry points, simply thinking functions, with very explicit inputs and very explicit output structure, which, of course, provides the data encapsulation that we need for the safe multi-threaded access. Now, a game object can register with multiple features. They can be statically determined what features it needs to register, or also, if we add a dynamic component, we can then register it dynamically with the appropriate feature. So if we look at this hunter lady, we register with a simulated cloth feature renderer, we register with skinned feature renderer, and we register with customizable gear renderer. Now, we provided an interface for those entry points, as I've mentioned, with very strict rules for what data they're allowed to read and write. This encapsulation is what allows us to actually ensure safe access. They can only read render node data, the view, the frame nodes, and cached static data. The later was done to automatically ensure that we don't overwrite any data, because again, these are going to run in parallel. Since you're only writing output to frame packet, the feature writers automatically get double buffered synchronization and don't have to worry about it themselves. Now, the core architecture generates jobs for every phase that extract, prepare, and submit. And this jobification is done automatically. The reason this is so important is because throughout development of our game, we continuously added, removed features. We added platforms fairly late in development. And we also had to go back and rejigger the load balancing for existing platforms. But none of the leaf feature codes was affected, which was awesome. Now here's the set of entry points for feature renders our interface provides. If you can't read all of the text, don't worry about it. You can look up the slides later. It's just to give you an idea of the sort of level of details. These entry points map to each phase. This is the extract, the prepare, and then the submit. Now for extract and prepare, we had entry points that operated only on individual render nodes. And these were the bread and butter extract and prepare entry points. This is essentially one render node at a time for one specific render object, in this case, a simulated cloth. There were cases, however, when you had to do operations on all of the visible elements of the same feature for a given view. This is the case of the LOD bucketing, let's say for cloth or for skinned elements. And so we added entry points to allow you to do that, to essentially use on individual view packets. Then, of course, you also wanted to do global operations. You wanted to look at all of the visible elements across all of the views for the specific feature, and then basically operate on that data to do a more frame global operations. Now, all of these are running as individual jobs concurrently at once. How do we deal with the concurrency issues on the feature renderer level? We split up the operations by frequency of access. This is the view, frame, and object. And this is what allowed us to share data across different views, across different render objects to save memory in the frame packet. So like I said, we only need one copy of skinning matrices. We also allow sharing across objects. It also allowed us to save performance, since, of course, we only want to compute the complex data once for the frequency that we use it. The core architecture uses sync primitives to ensure safe access. Now, when feature renderers fill out the function called extract per frame, they don't need to worry about anything related to the jobification. They don't need to worry that that job will actually execute, let's say, from shadow view number 1, concurrently from player view, and maybe shadow view number 2. It is important to use, however, a very performance synchronization method, because as you remember, we're operating on a ton of visible elements at once. And so we can't afford any heavy locking scheme for the high frequency operation per frame. And so in our case, this frequency is controlled by the individual render nodes. And we can have tens and tens of jobs vying for the same element. In this case, this is the early in development example of using simple locks. You can have essentially the wall of red is your locks. This is how often you are wasting performance by doing that synchronization in a very non-performant way. This is, of course, not what we shipped with. Instead, we developed custom lockless synchronization primitives for the render nodes. We used an interlock bit vector, and then we essentially used a hashed render node, hashing it to a key during synchronization. The key varied by frequency of access. Now, one word of caution is that although lockless primitives are superb for performance once you get them right, to get them right, you get the Schrodinger bugs. This is your, oh, holy shit, I can't really handle this because the moment I start debugging around at printf, the thing disappears. So timing-related bugs due to lockless primitives can be quite interesting to debug and get correct. So in our case, we ran extract and prepare per frame operations that will do the expensive computations only if that element is visible in any of the views. In this case, for the lockless primitives, we essentially hashed it to the per frame node axis. This was unique to all objects that are registered in the renderer. For per game objects, so for example, in that case of the hunter that I was showing you, we wanted to compute a lot of the computations once, even though we had a number of different features for that game object. Again, skinning, cloth simulation, but we also did dynamic AO for the objects. We also were computing forward light probes. And like I was saying, we were running a bunch of animation jobs for visible elements. And so in that case, we computed that using the lockless sync primitives that were based on the skeleton hash, since that skeleton was unique for that specific game object. So let's look at a couple of feature examples. Simple one is a static projective decal. So here is like A to B. You can kind of see that in the image appearing. This is very simple. They're static. They never change. They don't need to extract anything. They don't need to prepare anything. So we simply need to render them using the submit node entry point. Now, as an optimization, because you know you're going to render a bunch of decals at once, we can also set up all the render states in the block begin and then in block end. The next level is skin feature render. Now, of course, this one needs to extract a bunch of data from game state. This is my transforms, my object properties in extract phase. In Prepare, like we were mentioning, we're going to do all of the per-object computations for bones based on the object LOD. We're going to generate our GPU registers, dual quaternion data, et cetera, the dynamic AO, light probes. Now, both Extract and Prepare use render node entry points, and they only rely on per-object data in computation to save essentially the representation and work. Now, and of course, we render our skinned element using the submit node entry point. Now, one of the most complex features is cloth feature renderer. This feature renderer ended up implementing almost every single entry point that we have in the engine. It iterates over all of the possible cloths at the start of the frame to reset its simulation state. It then extracts the skinning data, object transforms, the collider transforms for the cloth elements in the extract per node entry points. In the finalize on the entire frame, we actually run the LOD bucketing to constrain the cloth simulation elements to high, low, and GPU skinned. High-low simulation and GPU skin buckets, because again, remember, we're going to only want to do 2 milliseconds worth of simulation. Then in Prepare entry points, we're going to update the cloth colliders. We're going to do the gather for static and dynamic environment shapes and dynamic objects to collide cloth elements with. We're going to launch and run Havoc cloth solver jobs. We're going to synchronize on the final cloth world updates for the whole frame. We're going to update the cloth vertex buffers, and so forth. So you can see that the feature renderer can map to a very complex execution pattern. And of course, to render individual cloth element, we're going to run the submit point. So at this point, we have a job pipeline that submits general views. This is pretty far from the real work, of course, because we don't render with the same shader in the same set of render targets. So what we really want is to selectively select what objects we're going to render using the right shader techniques when we want to render that pass. And of course, we want to make this process automatic and super extensible. So this is the CPU submit. The point of CPU submit is to generate GPU commands for that frame. The first workload we're going to do is run the player view submit script. I call it script, but it's not actually executing any Lua or specific script language. Before we break down how that works, let's take a quick look at how the GPU frame is structured. If we look at breakdown of the frame, you'll see that we build a frame from a number of passes. Here's the passes on the right. Note that these passes are actually different depending what data you have visible in the frame. We typically start computing GPU updates for all of the particles and the GPU-driven elements. We render the atmosphere pass. We do the G-buffer pass. This is the depth pre-pass, the G-buffer opaque, the decals. We're going to do shadows. This is the generate, cascade, and local light shadows views and apply them. We're going to do the lighting pass, the additive decals, the transparency pass. Of course, we're going to render geometry to light shafts occlusion buffers for the sweet God rays. And then we're going to punch everything up by rendering lens flares. And then finally, we have the complete frame, and that's our final composite. So what does it take to submit this? Now, the high-level submission is fairly branchy, complex code. We need to determine based on game state, are we in first-person mode, are we in third-person mode, do we have shadows, do we have cinematic, high-quality subsurface scattering, or special post-processing passes. And the script executes essentially high-level rendering directives. It's important to say that it interleaves global state. This is your render targets, binds, clear, expensive state for aliasing, decompressing, and resolves. And those go directly to the main GPU ring, command ring buffer. We also store the global state for like frame registers, views, et cetera, also in the global ring buffer. This is the direct insertion. Now, at the same time, every time we want to issue one of these passes that you see on the left here, we're going to issue a submit view directive. This is a call from the high-level script to the core architecture that is designed to generate GPU commands for that view. From the perspective of people who write the high-level script, it's cross-platform, it is not jobified, and of course, it's very simple to create. It's just a couple of functions, literally. Which means that if we need to adjust the job granularity, again, this also doesn't need to change. Under the hood, the core renderer architecture converts this directive to a set of submit view jobs. And the rule of converting jobs varied per platform due to our desire to have optimal GPU occupancy and keep the game latency low. I'll talk about that in a few minutes. If we come back to our previous design for the pipeline execution, where does GPU fit into this picture? So what we do is essentially thread the rendering execution to start feeding the GPU right away, to have GPU crunch on the data as quickly as possible to get our frame to flip at the very next V-blank that we're able to hit. And ultimately, what we want to do is figure out how to fire up the submit view jobs using the feature renderer entry points that I mentioned for the submit node from the high-level submit pipeline. What we need to do is distinguish which visible elements from this frame packet that we have need to be submitted to, like, let's say, a decal stage, using the transparent or transparency using this high-level script view. And so again, as I mentioned, the high-level script is transparent, and it's organized in phases, where essentially each phase is a sequential combo of required passes. This is shading pass, tone mapping, resolve, et cetera, and data-driven dynamic passes. This is the render stage directives. Now, render stages are a mechanism. Essentially, think of it as a filter for submits. At its core, it's about filtering the right shader, so finding the right shader to submit for that phase, and finding the right mesh set to submit for that phase using that shader. So how do we go about it? Each object can subscribe dynamically or statically to a render stage, either at registration or at any point. So for example, here, we activate our super. Right now, the object registers the transparent render stage for that character, and then we start rendering the transparent effects pass for that element dynamically. Now, to filter the list of visible elements in each stage, we use the view subscription for the render stage. Individual views will say, hey, I actually support this or I do not. So for example, shadow view only supports the shadow generation render stage, which means it will only select the shadow generation shaders and it will only render shadow casters. A player view will support a variety of render stages. So visible elements will render G-buffer, decals, transparents, etc. When we execute those high-level directives that I mentioned earlier, essentially the test that we do on a high-level job creation is, does this view subscribe to the render stage, and do we have any visible elements that also subscribe to the same render stage? So how do we get that information about the elements? Well, we have a custom shader language that we developed for Destiny called TFX, for Tiger Effects. And we basically have each technique specify what render stage it belongs to. Once this is specified, we can actually offline compute for every single mesh that this element has an assigned shader for, and then create containers for each render stage. For example, mesh 1, 2, 3 will render to the transparent stage, and mesh 5, 6, 8 will render to G-buffer. This gives us constant access at runtime, very small data representation, which means we have super cache coherent execution at the submit jobs. Once the visibility returns the visible list, we're going to go and essentially populate the set of render stage nodes. Now, what we do is, as I mentioned, we run the populate render nodes job, and now on top of the view nodes that I mentioned, we also will use render stage subscription data to create blocks for individual submit stage. This is what the submit jobs will iterate on. Super cache coherent and quick to do. And again, this is going to be selected for the specific view that needed. Now, these submit nodes is actually how we run all of the sorting. Remember, transparents need to render in a very specific order, back to front. Great. We only sort the submit nodes, and we're good to go. If we want to sort G-buffer submission to be per feature for coherency, great. We'll create a submit sort metric to essentially use that to control it per render stage. Now, any object can register as many submit nodes as we want, because we allow it essentially based on the limits of memory. So if you wanted an object that, let's say, had 5 transparent elements, and you wanted to essentially sort it individually for the mesh parts, create 5 submit nodes. You're good to go. Then you are sorting and submitting each individual mesh part in the right order, which was super useful. Our artists loved it for creating higher quality transparency. And of course, the sorts themselves are super fast because they're operating on tiny elements in cache coherent submit blocks. And here's an example of the byte size for the individual render nodes. As you see, we kept them really lean and mean. And so that gives us essentially really fast cache coherent core renderer workload execution for our sorts, our allocations, all of the traversal for extract, prepare, and submit. Now, we duplicate some of the data, as I mentioned, across the view, frame, and submit nodes, again, so the data is already in cache when we're iterating on them. Now, when we say on a high-level submit node that we're going to render first cascade shadow view, the core system takes that function, which is literally submit cascade view for render stage, and it's going to generate submit jobs for the cascade shadow view job chain using the view packet's render stage submit node block. Internally, what it does is essentially grabs the appropriate submit node block for that view. So here's an example. And then we're going to execute the appropriate render objects using essentially the view node, the frame node, the cache static data. And of course, as I mentioned, we don't allow access to game state because simulation is running concurrently. The core system will actually split up the high-level directives into separate jobs. So for example, we're going to group set of nodes. Here you see color-coded example of the batching. One set of, let's say, 2 submit nodes go into one job, 3 go into a separate job within the render stage and across render stages. And we'll talk about that batching in a second. So feature submits are already grouped by the code path similarity, by the data representation similarity. We can sort the submit blocks by the, essentially, features type if the render stage allows it. We're only executing using local state using specific stages kernels. I realized this fairly late in the architecture design, but I realized this looks very similar to GPU architecture. I guess I came from the GPU hardware group from AMD, so I must have been influenced a little bit by that. And so all of this allows us to run coherent execution in the stage jobs. And in some ways, we have a lot to thank SPU for because, of course, being able to fit that into those precious 256 kilobytes is what forced us to go down this path. But it maps very well to data parallel processing. Our submit jobs just became fully streamlined kernel processors. So when you put all of this together across all views, all render stages, all render features, you come back to that jobified renderer pipeline. So now that we have the core renderer architecture established, we can start adding bells and whistles to it. The nice part about getting to this point is from now onward, none of the leaf features are touched, and you can reconfigure whatever you want in the core area. And actually, throughout Destiny's ship cycle, we tweaked, pruned, batched, and otherwise massaged job dependencies, synchronization, occupancy rules, distribution across CPU and GPU continuously to make sure that we have super low latency and fast execution. And we didn't have to rewrite any of the features. I'm personally very happy about that since I own a bunch of leaf features, and I'm lazy. So now that we have this, what other cool stuff we can do with our architecture to make it even more effective? Render jitter and rendering latency reduction comes to mind. Now, we had to implement a number of these techniques. Unfortunately, due to time, I won't be able to dig super deeply into this, but I added some slides in more details in the published version. Now, to keep the GPU maximally occupied and our game latency minimal, we multi-threaded our submit, as I mentioned earlier. We also implemented custom CPU and GPU dynamic load balancing to flush out the GPU bubbles. Efficient command buffer was crucial. Once you've generated a command buffer, you need to get it to the GPU as soon as possible. We also used asynchronous swapping on platforms that supported it. Make sure not to block your CPU if you don't have to. And we also implemented a jitter reduction technique that essentially kept a constant present interval, but recovered latency when it went too far by reducing that present interval. So with all of this happening under the hood, we were able to do whatever we needed to. GPU occupancy is a very interesting subject, and like I said, this will be somewhat high level. We need to keep in mind the following information about the GPU occupancy. When did we generate the GPU command buffer from the CPU? If we take too long, we obviously don't start the work. And when the GPU finished working on the previous frame? So, to help answer a lot of these questions, we actually implemented custom tracking of GPU idle. There are a number of counters, and I'll include it in the published presentation, that your engine can query to get the information about the idle blocks on the GPU. Now, these exposed counters are a little tweaky and not super reliable on all platforms, but still, I highly recommend you use it. Anytime you track it throughout your performance run and you start seeing big GPU idle reports, you know you're starving your GPU, and you need to address it. So here's a timing capture from the Xbox profiler using a development mode. Now, in this case, we're going to start CPU submission here, and we're going to start executing, let's say, serialized command. In our case, that actually meant a few jobs, but every one of these jobs is using a single-threaded device. And so you can see that we ultimately start working on the processing of these GPU command buffers fairly early. We're able to feed the GPU quickly here. But we're done with the generation of the GPU commands all the way over here. This took a fairly large window. And basically, you right away know the serialized submit takes a very long time to execute on CPU. Also bad for game latency because we can't unblock the submit loop for the next one. And this is where we also call or present. Now, you can see that the GPU starts working on submitted draw calls here. And you can see that there's a ton of bubbles in the GPU timeline. This is the GPU execution. Now, of course, this timeline means you're starving your GPU. You're wasting milliseconds. And so it's negatively affecting the rendering latency. Obviously, we can't ship with that mess. And so what do we do to keep GPU occupied? It's a fairly complex subject, but in the very least, you want to multi-thread your submit. You want to make sure to flush your command buffers as soon as you got them. This can be quite tricky on some platforms where you need to essentially run a watchdog thread to pipe out whenever the GPU command buffer is ready, flush it down to the GPU. And you also need to muck with your submit jobs, and I'll talk about that in a second, to make sure that they're executing a proper tandem of CPU and GPU workloads. And lastly, V-blank synchronization is very important. You want to offset your computations based on V-blank. Now, in order to get the GPU work complete, we want to make sure once that work is complete, we're ready to flip it and display it to the player. Now, the good news is a lot of consoles allow you to track V-blank events, and you know exactly when they occurred. That's wonderful. Other consoles, and PC in particular, do not allow that, which is terrible, and they require manual work. And so, for example, we implemented a separate thread that sits and waits for V-blank event. Now, on PC, watch out for a deadlock whenever you resize a window or do essentially a full screen change, because both present threads and the V-blank wait threads are going to want to change your window pause. That little tip can save you a week. So, how do we go about getting our GPU occupancy in an optimal way? The quicker we can get commands to the GPU, the better off we are. So in this case, we're going to start executing multi-threaded submit using deferred command lists or command buffers. And so once we're done, we're going to run a lot of these commands to submit to the GPU. Now, the game latency is reduced. Look how much quicker we're able to complete the work here. And then we present the frame a lot faster. We might even run so quick that we're actually going to run the GPU a little late. But it's a solid, it's a solid wall of work. If you notice here, we have 0 bubbles in this execution. And so that's exactly what we want. GPU is continuously working, and it's not resting until we're done. So how do we go about doing this wall of solid work? Now, important thing about multi-threaded submit is not just, hey, you need to generate a bunch of command buffers. You need to submit them to the GPU in a particular order. We can't flush the transparent jobs to the GPU before your G-buffer jobs have completed. That's going to generate visual errors. And so we need to establish a very explicit synchronization for the flushing of the command buffers. So we allocate the command buffers from that high-level submit code. We execute submit jobs, and we flush them to the GPU in the same order that we've allocated. Because the submit high-level code is going to be in order of GPU expectancy, we're going to ensure that we're going to process them on GPU in order. Now, this is, remember that some high-level script that I mentioned where we do a render view per stage for each feature renderer. What we actually do for this directive is we map each request to a set of asynchronous command buffers or deferred command lists on the platforms that call it that way. These commands are either directly inserted into the GPU command ring buffer, or we use a custom indirection, for example, on Xbox 360. And there's a lot of trickery there for the actual flushing. I'll include it in the published slides. But essentially, think of it as each request generates a synchronous command list in concurrent jobs. And so we can jobify, as I mentioned, using the submit node blocks. And we group them by essentially render feature type and the render stage. And it's important, as I said, that they're flushed in the order of creation. And so each submit node block here will map to a single submit job and a single command buffer for the execution. Well, as I mentioned, we need an optimal cadence of CPU and GPU workload. What I mean by that is you want to run really light CPU workloads first to get your GPU working. You want to submit, let's say, typically a good example is my environment depth prepass. And so super easy to submit for terrain and environment instances. It requires very little logic, but GPU is now busy. And then we're going to run a more complex, let's say, G-buffer workload for characters that might take a little more time on CPU, but GPU is still busy. We're OK. And then we're going to render the heavy GPU work and then submit all of the computations for the rest of the pipeline. So in our case, we allow the features and render stages to supply a cost metric, essentially mapping it to the cost on CPU and GPU. And then we sorted that cost metric for the conversion of the submit jobs. And so you can basically automatically fine-tune the dynamic load balancing both for GPU and CPU occupancy for each platform, because that cost metric can be switched on every platform per feature, per stage. Creates a little array of little descriptors, essentially heavy CPU, light CPU, medium CPU, light CPU, heavy GPU, light GPU, et cetera, coarse-grained. But it really allows you to fine-tune to create that wall of GPU workloads. Which brings us to another topic, and then dynamic load balancing. Now, we needed to attack an axis on CPU, right? Because if in a data-driven pipeline, we can easily be doomed to a very high job overhead cost. And so, of course, the naive approach to all of this jobification is jobify the hell out of it. Move everything into a separate job. Yay. We did start with that. And we then discovered that on last-gen Platts, we had about 7 milliseconds of job overhead. And we cried a few crocodile tears because 7 milliseconds out of, let's say, 30 millisecond workload is a fairly high percentage. And so that was bad. We need to get rid of that. Also, you noticed, as I was saying, some of the features do a lot of work. Others are pretty light. My terrain doesn't really do anything in extract. My skin does a lot. So, again, using the same concept, we allow specification of granularity of workloads per phase for each feature. Each feature renderer then supplies a simple metric heuristic that says, for extract, I'm a light one, or I need to run in a standalone job. And then the core render architecture uses that information and batches light features for a bunch of different render objects together. And then maybe it'll take some heavy features, my scanned object or my cloth object, and move it out to a separate job. And so essentially, this allows you to have similarly automatic load balancing. And again, you can tweak this cost per platform. If I suddenly start doing a lot more work for terrain, maybe for PS4, fine, I'll just change that metric as reported on the PS4. Now, another nice thing about that metric is similarly, you can also have the feature report which unit it wants to execute on. And so again, it can say, hey, for phase A, I'm going to execute on SPU or on CPU, or PPU in this case. And then, of course, the core render architecture will schedule the heterogeneous execution based on that metric. And so we mostly use this functionality for extract phase because that's when we can go wide across all of the units. Typically, simulation ran fairly heavily on PPU, for example, and so we left it alone for those phases. And so here's an example, again, from that PS3 execution. So our PPU, our SPU, and if we look at extract phase, you see that the workload is spread equally across all of the units. And that's the example where we allowed some of the heavier features, say whichever unit they want to run on. And then we looked at the availability of jobs scheduled on that unit, and then simply moved that job to that workload to that unit. So I know this was a really easy topic. You guys lasted a good amount. I'm very proud of every one of you and my ability to speak quickly. So it's not a complete system description. This is not a spec. We barely touched on some of the more complex aspects of our system, but you should have a pretty good idea of our overall design of the system. So back to our goals. How did we do? We did deliver low latency, stable, highly scalable renderer that executed on all of our shipping platforms, multiple console generation, yay. It enabled us to ship the game. Again, remember that big goal. the vast majority of our feature code, things that aren't ESRAM, EDRAM, ugliness, etc., were all cross-platform code. The vast majority of optimizations for the core render architecture didn't touch that. So I'd say ship it, but we already have. Now, multi-threading the renderer was key to shipping Destiny. You saw that thick wall of occupancy on PS3. We wouldn't be able to support some of these more challenging platforms. Now, we can use this kernel processing and actually extend it in the future if we have some spare GPU to run on the compute units. We already have kernel processing. Of course, we don't really have spare GPU, but if we could, we would. And so the architecture, scalability, and dynamic load balancing, cache-coherent data access, heterogeneous support is what allowed us to achieve low latency despite very heavy workloads across the board. So again, coming back to that takeaway, if there's anything I want you to walk away from, is if you do this similar data-driven pipelined architecture and then hide all of the complexity from the individual feature writers, you can write a ton of features. You can re-optimize whatever you want, and both will be happy and not bothered with that complexity. So a little plug, if you like what you heard and you were excited about the work that we've done, we're hiring. Many people contributed to the graphics of Destiny. Many people contributed to the different aspects of the architecture. And we have an incredible team of engineers and artists and designers that created this game. So stop by and let us know if you're interested. So we're out of time, but we're the last talk. So if you guys have questions, feel free to ask them. And while you're asking the questions, the slides will be loaded up there, and then if you have questions, my email and Twitter is up there. And student.